Welcome everyone. For today's prep, we're going to see how to graphically find the intervals of increase decrease for a function. So by the end of this lesson, what are we going to do? Well, we'll be able to locate the intervals of increase and the intervals of decrease given the graph of some function. And then we'll also see how to locate what we call the local maximums and the local minimums given the graph of a function. And we're going to define all these terms as well. So let's start with increase and decrease. What do we mean by a function increasing and what do we mean by a function decreasing? So let's look at our definition. So let's start with increasing on an interval. So we say a function's increasing on an interval if the graph continuously rises. It goes up as x goes from left to right on that interval. So a way to think of this is, or the precise definition of this using inequalities, is that if we take any two x values from that interval, and we pick one to be less than the other, and we plug both of those x values into our function, well then the function value goes up. So the one function value is bigger than the other function value. Now, graphically what this would look like is our curve is going to have some kind of upward trend. So it's moving up like this. Now, what about decreasing on an interval? Well, in this case, the graph continuously falls as x goes from left to right. So it's going to have a downward trend. So it'll look something. It'll have this overall look. Now, the precise definition with inequalities is, again, we pick two x values on the interval, and we make one of them smaller than the other one, and we plug both of those x values into our function. Well, if it's a decreasing function, what that means is the inequality gets reversed. So the function value goes down. It decreases. All right. So graphically, let's see what this starts to look like. So we're going to look at an example here. Same function, but we're going to look at three different places along the graph. So we're going to figure out if this graph, or at the function at each of these points, is increasing, decreasing, or neither. All right, so, and the way we're going to do this is by drawing our tangent line. Kind of gives us the trend of what our function's doing at that specific point. So let's look at the first graph here. And we're interested in this specific point. So let's draw the tangent line. And looks something like that. So there's our tangent line for this point. And we see that the tangent line has that upward trend. It's going up. So we would say this function is increasing at x equals c. It's increasing at this point. Now, let's jump over to this one over here. Same curve. Now we're just looking at a different point. So again, let's draw the tangent line. So something like that. Doesn't look too bad. So we've got our tangent line over here. And what we see is that, well, the graph is falling. It's moving down. So it has a decreasing trend. So we would say this function is decreasing at x equals c. Now what's going on for that graph in the middle? So again, find the point that we're interested in, draw the tangent line, and at this point, the tangent line is going to be horizontal. So we have a horizontal tangent line here. So what that means is the graph is flat at that point. So it's not really increasing and it's not really decreasing. So it's kind of like in between. So we would say it's neither. Okay, it's a flat graph. But something interesting is happening here. And we see that this point is actually a low point on the graph. So those places are special, and that's going to be our next definition. So we call those types of places relative minimums or local minimums. And in the case of a high point, we call it a relative max or a local max. So let's look at a couple examples here, a couple graphs, and then we'll go back to the definitions. So the first graph here, we have this point at x equals c, and we see in this case that it has a horizontal tangent line there. But if we were standing on top of that point, what we'd see is that this is a local maximum at x equals c. So if we were standing up here, it'd be like we're on a mountain peak, and it's downhill in both directions. And for the other curve, this is an example of what a local minimum would look like at x equals c. And a way to think of a local minimum is if you were to standing at that point, it's uphill in both directions. Now, this word local, what does that mean? Well, it means we're only looking in kind of the immediate surrounding area. So maybe if we were walking along the curve, maybe there's a section of the curve that eventually, gets lower. But what we're doing is we're just considering this immediate surrounding area. Same thing over here. We're just looking in the surrounding area. So there might be sections of the curve that eventually go up, but right here, that is a high point along our curve. So we're looking in just the immediate surrounding area, the neighborhood. So the precise definition using inequalities, we say that a local maximum value of our function is the function value f of c, and f of c is greater than or equal to all of the surrounding function values, kind of for x near c. So for all these x values that are near c, that one point is the biggest. And then a local minimum, well, it's a value of our function. So we plug the number c into our function. And what happens is that function value is smaller than all of the surrounding function values. So any x value that you plug in that's close to c is going to be a little bit bigger. So again, if we look at just the x values that are surrounding it, the lowest one is that point at x equals c. All right. So that's the definitions. Now let's try an example. So we're going to look at example 2. And in this example, we're given the graph of a function y equals f of x. And we're going to use this graph to find the intervals of increase, the intervals of decrease, and then we're also going to locate the local maximums and local minimums. So let's start with let's look at the graph first. Let's kind of take it in. And when we look at a graph, you want to start by, I think it's a little easier to find where the local maximums and the local minimums occur. Your eye's kind of drawn to those places. And we're going to kind of categorize these in two ways. So we're going to find the x values. Where function f, where f of x has, now we're looking for two things. We want to find the x values where our function has a horizontal tangent line, and we also want to find the x values where our function has a sharp change in slope. So we know sharp changes in slope happen when we have a non-differentiable point. So these are the two things we want to look for. So we want to find the x values where our function has either a horizontal tangent line or a non-differentiable point. So let's start with the horizontal tangent lines. So these are all the places where our graph has a nice kind of rounded, flattens out, but has a nice rounded shape to it. So we see there's three locations where this happens. We have a horizontal tangent right there. We have a horizontal tangent right here. And we have a horizontal tangent down over here. And so those happen. We want to know the x values where these points happen. So we have our x-axis here. So let's indicate those points along the x-axis as well. So we've got something happen at -2. We've got something happening at 0. And then we've got something happening at x equals 3. So let's write those down. We have a horizontal tangent line at x equals -2, at x equals 0, and x equals 3. Okay. So those three values are important. They're going to be important for helping us find the local maxes and mins, but also finding the intervals of increase, decrease. We also want to look at non-differentiable points. And in this case, there's one non-differentiable point. So this is where our graph usually has a sharp change in the slope. And for this one, we see it right there at -1. And again, it's an important point, so let's indicate that along our x-axis here. So we have a non-differentiable point at x equals -1. All right, so what we have is we have our x-axis, and we've kind of sliced it up into a few different sections. So what are the sections here for our x-axis? Well, we've got this piece of our x-axis. We've got this piece of our x-axis. We've got this little piece. Then we've got this piece right here. And then finally, we've got the piece that just keeps going all the way to the right. So these slices that we've made along our x-axis, what they've done is they've broken the x-axis up into intervals. And so what we're going to do is we're going to look at each of these intervals. So let's start with the first interval. What we see is that on this interval, the graph is moving upward. So there it is increasing. On the next interval, between -2 and -1, we see that our graph is moving down. So on this interval, our graph is decreasing. And then from -1 to 0, well, what's going on? The graph is going back up. So it's increasing again. And then from 0 to 3, if we look on that section of our curve, well, it's going back down. So decreasing. And then finally, once we get to the point at x equals 3, the graph looks like it then just keeps increasing forever. So what we've done is we've found the intervals where our function is increasing and where it's decreasing. So let's formally write this out. So we're going to say it's increasing on what intervals? Well, let's start with this first interval. So it's everything up to -2. So the way we indicate that is it's going from -infinity to -2. So you want to think of this direction of our x-axis, that goes off to -infinity, and this direction goes off to positive infinity. Okay, so that's one interval of increase. Then we found in between -1 and 0. It's increasing there. And then finally, from 3 onwards, so 3 to infinity, is another interval of increase. And we're using open intervals, which means we're using parentheses at the endpoints. And then we found it was decreasing. There were 2 intervals that we found. So let's write those out. All right, so where did we find? Well, we found decreasing in here between -2 and -1. And then we found decreasing here from 0 to 3. Okay, so we got our intervals of increase, decrease. So now we want to look at We just want to find where this function has a local max and local min. And we've kind of already identified these points, but now we just want to actually classify them. So if we're looking at the graph here, we see that we're looking for high points and low points on our graph. So we see a high point right here. So this is a local max. And again, imagine if you were standing at that point, it's downhill in both directions. Sure, if you walk far enough, eventually you get to some higher points, but in the immediate surrounding area, that's the highest point that you can be at. Okay. Well, we also have a local max right over here. So this point is also a local max, because if you were standing at that point, it's downhill in both directions in the immediate surrounding area. Sure, if you walk far enough, then eventually you find some other higher places, but right around that point, that's as high as you can get. And then what about some local mins? Well, we see a local min right here, kind of probably the most obvious one. So that's a local min point on our graph. It's a low point. And a way to think of minimums is, again, if you were standing at that point, it's uphill in both directions. And again, it's a local min because, sure, if you walk far enough along the curve, maybe you will encounter some points that eventually get lower than it. So, there's this section here where they're lower, but in the immediate area there, that's as low as you can get. Now, there's one other local min, and that's at this point right here. So even though it's not a nice rounded location, it's a non-differentiable point there, it's still a local min. It's a low point on our graph. And that's because if you were at that point, well, it's uphill in both directions. So let's write out let's make sure we answer the question, what are the x values where we have a local max, and what are the x values where we have a local min? And what we're going to see is it's not a coincidence that the places where we have a horizontal tangent line and places where we have non-differentiable points, well, those are the places where we have mins and maxes. So for our case, we have a local max at, what are the values? So we said we had a local max right here, and that happens at -2. And then we said we also had a local max right here, which happens at x equals 0. And then local min, well, we have two of those. So one of them at x equals -1, and then the other at x equals 3. All right, so we're going to try a few more examples like this in class. And then we'll see how we can do this type of analysis where we might not have the graph of the function, but we're going to see how to do it using the first derivative. So we'll see you then. Bye-bye.